Yo, what up? Today we're going to be designing a distributed rate limiter. So what even is a rate limiter? Well, to put it simply, it's a way to limit the number of client requests over a specified period. For example, let's say we're running a social media app. We don't want a user to be able to post like 500 times a second. We want to limit it to a reasonable amount so that the platform doesn't get abused, the servers aren't overloaded, and so infrastructure costs aren't necessarily high. Now, when we actually want to create a rate limiter, a decision we need to make is where we want to put the rate limiter. So the first is over at the client. Let's go ahead and look at the pros and cons. The first pro is that it's simple because you can implement a lot of things on the front end, like loading buttons. It's also instant because the check runs on the user's own device, so a block click never even leaves the phone. The main con though is that it's not secure because the check is running on a device we don't control, and this means anyone can skip the front end entirely and hit the servers directly with a script. The second place we can place our rate limiter is over at the server, and this is usually the better option. First, because it's much more secure. The server is fully under our control. Everything is also centralized, so we don't have to worry about scripts bypassing our front end. The only thing though is that we need to take into account server load, eventual scaling. It's overall way more complex than the client side. Okay, moving on. Since we decided on where we're going to build our rate limiter, we need to now decide on how. So there are several rate limiter algos out there, but for this video, we're going to stick with the token bucket algo, which is both simple and effective. The easiest way to explain token bucket is that it's kind of similar to elixir collectors in Clash of Clans. It takes in two params, the bucket capacity and the refill rate. So basically the elixir collector, or bucket in this case, will keep refilling tokens at a rate until it hits its capacity, after which it'll max out at its capacity. Now, if a request comes in after, then it'll need a token to go through, or else it'll get rejected. The pros and cons of this algo are that it's very easy to implement, it's memory efficient, and it also allows for a burst of traffic, but it's challenging to tune. Okay, now that we've discussed the why, where, and how of the rate limiter at this point, we're basically ready to design the high-level architecture. But before we go any further, let's talk about some of the important challenges we'll be facing and need to address. The first issue is called the race condition, which happens when two operations race for shared data. For example, imagine our rate limiter bucket only has one token left, and two requests arrive at the same time. If both requests check the bucket before either one updates it, they'll both see that a token is available, and because of that, both will get allowed through, even though only one should have been accepted. Now the second issue is related to speed. The limiter runs on every single request to the product before any real work happens, and every one of those requests needs to read and update a bucket. The buckets are really just little counters, so whenever these counters live, has to answer in a fraction of a millisecond. Now the instinct might be to reach for a normal database like Postgres, but databases write to disk, and disk is slow, so we'd essentially be adding a disk trip to every request just to decide yes or no. And the important thing to note here is that we don't even need what a database sells. Databases are careful with your data, so it's never ever lost, but our counters are temporary by design. Buckets refill themselves within a minute anyway, so losing them isn't even a big deal. The third issue is synchronization. At scale, we won't have just one rate limiter, we'll have multiple, and the moment there are multiple, they need to stay in sync. On top of that, if the web tier is stateless, meaning clients won't always hit the same server, we have to be prepared for requests landing on different rate limiters. One solution to this is called sticky sessions, which ensures the client always sends traffic to the same rate limiter, but this isn't really scalable or flexible. So let's look at the three issues together. We need shared data that doesn't get corrupted when things race, data that can be read and written really fast, and data that every single server agrees on. Luckily for us, there's one tool that answers all three. It's called Redis. Okay, so Redis is basically a Python dict in RAM with a network cable, and importantly, it's single-threaded. That combination deals with all three of our issues. For the race, our entire token bucket logic becomes a tiny Lua script that Redis executes as one atomic operation. And since single-threaded means Redis runs one command at a time, nothing can ever interleave with our script. For speed, it's RAM all the way, no disk anywhere in the path, which is fine because, like we said, our counters are allowed to be temporary anyway. And finally, for synchronization, Redis becomes the centralized store. The apps run the code, Redis holds the state, and there's exactly one copy of every counter, no matter how many servers we run. Okay, now that we've covered the three issues, let's start building out the diagram. I'm going to build the whole thing on this canvas, and every time the design works, I'm going to show you the exact case where it stops working, and then I'll try to fix it. So let's go ahead and build it the most obvious way first. I'm representing the limiter as its own shape so we can talk about it, but this is not a separate machine. It's code living inside the server. Now a little bit about these servers. Each one is going to be a Python app built with FastAPI, and the one FastAPI feature that matters here is middleware, because it lets us register code that runs before every endpoint. Now an endpoint just means one specific thing the server can do, like search or upload, named by the URL path. So one server has many endpoints. The hexagon here is one Python function standing in front of all of them, and when we add more servers later, each one will carry its own copy of the layer. So a request arrives, and then the middleware asks one question. Does this callers bucket have a token? Now if it does, it takes one, and the request goes through the endpoint. If it doesn't, the endpoint never runs, and the client gets back a 429. A couple of notes from the actual code. First, we want to stay polite, so every rejection also tells the client when to retry in seconds. Send in a response header called retry after. Second, we're not actually refilling buckets in the background like you might expect. It's more of a lazy refill. So when a request arrives, we look at the clock, see how much time has passed since we last touched this bucket, multiply that by the refill rate, add that many tokens, and cap it at the capacity. And one more thing, the two params we chose apply to many buckets. Every client gets their own. So person A burning through their 20 tokens doesn't touch person B's. One small thing to hold on to before we move on. All these buckets are just a dictionary in the server's memory. And that's fine for one server, but it's quite dangerous for multiple, and I'll show the reason why later. Okay, so the limiter works, but how do we make this work at scale? Let's go ahead and try the natural move first. So we have multiple servers now. Identical copies with the same image, code, and middleware layer inside. Right now we're basically copy-paste scaling. But clients need one address, not a list of servers to try, so we'll need a load balancer to split the traffic. A little about Nginx. Its purpose here is to just receive a request, forward it to the next server in rotation, and relay the answer back. A load balancer is round robin style, and if we notice the topology, the load balancer is the only way in, so this adds security. Okay, now at this point, we have the same middleware in both servers. This means each server also carries its own private dictionary of buckets right now. And each server will enforce its own limit against its own notepad. This seems alright at first, but let me use an example to demonstrate a problem that may arise. Let's say we have 2 servers, 8 requests, with a limit of 4. Round robin will split the requests 4 and 4, and this will pass even though it shouldn't. The solution to this is that the counters must live in exactly one place that every server shares. So let's move every bucket out of the servers into our shared store of choice, which is Redis. So now both servers read and write the same entry. Person A's tokens are one number in one place, and there's nothing left to disagree on. The servers at this moment are stateless. They hold code and no data. So adding server 3 or 10 or 50 is actually just copy-paste scaling. This one arrow is what makes horizontal scaling safe. Okay, let's call back to the race condition from the start of the video. This is where it actually shows up. So let's go ahead and first write down the code we would naturally write. First, we would read the bucket from Redis, and then we would decide in Python on the server, do the refill math, check if there's a token, subtract 1, and then after we do all of that, we would write the result back. So basically the process goes like read, decide, write. Now this is 2 network trips with a pause in the middle, and this pause is exactly where the 1 token story from earlier happens in real life. The 2 requests inside the gap at the same moment both read the same number and will overwrite each other. So let's go ahead and look at how we can fix this gap. Well, we know the answer is Redis, like I mentioned earlier, but why not something like locks? Okay, well, let's imagine using locks. Everyone will queue for the bucket. What will we do if the lock holder dies mid-hold? Instead of guarding this gap, it's way cleaner for us to just delete it. And this is where the Lua script in Redis I mentioned comes in. We want to move our entire logic from the servers to run inside Redis. And because like I said, Redis is single threaded and runs 1 command at a time, there will be no gap left to grace in. Evalsha, by the way, just means the script gets uploaded to Redis once, and every request after that sends its fingerprint instead of the whole script. So it's still 1 round trip. Okay, we've definitely made some progress. The rate limiter is correct and it scales. But right now every limit is hard-coded, and we have to rebuild and redeploy every server to make some changes. What happens if we have multiple endpoints and we need to account for different budgets? The answer to that is to create a state for the rules themselves. So what we're doing is moving the rules into a YAML file, which is just a plain text file anyone can read. Each endpoint we have will get its own budget, and there's going to be a default for anything not named. Let's look at how the apps will use it without getting slow. So every app will keep a copy of the rules in its own memory. That's a cache. And a little background task inside each app will reread the file every few seconds. So the hot path, the code running on every request, reads a dict that's already sitting in memory. We want it to never touch the disk. Now, it might look like we're adding state back into the apps, but it's fine, because these are configs, not counters. And a copy of a config being a few seconds stale is harmless. And this buys us something great, because I can open the file, change a limit from like 5 to 2, hit save, and within a few seconds, the servers are gonna start enforcing 2. No need to restart or redeploy. And one detail worth noting, it's important that the reload task is written so a broken edit can't hurt us. So just in case, like if the file doesn't parse, the app should just keep the last good rules until it does. There are also 2 things at the stage that are in the final coded version, which I'll link in the description. First, buckets are now per client per endpoint, so person A's search budget and their upload budget are gonna be separate bucket entries, 1 client, 1 bucket per endpoint. And second, since the limiter now knows each endpoint's budget, every response will carry it. There's a header with the limit and one with what's remaining, on top of the retry offer from earlier for rejections. Okay, so now that we've dealt with making rule changes effectively, is there any other way we can improve our current rate limiter? Well, let's look at where we're at right now and what a 429 actually costs, depending on the request. If, for instance, person A searches for something and we reject it, that's fine, because a search result is worthless to them 5 minutes from now anyways. But say like the request was send person B a notification or email this receipt. Nobody's gonna be there sitting waiting for it, and the work doesn't really expire. So rejecting that request doesn't protect anything, and it just loses work we could have done. What I'm getting at is we want to make the rate limiter smarter, and we want to be able to separate the requests that matter right now from ones that never can be delayed. Option 1 is everything we've built so far, and it stays the right answer for anything interactive. Option 2, though, is the new move, and it's for the fire and forget endpoints. When the bucket is empty, we don't refuse a work, we just queue it, and the middleware will push the job onto a list in Redis and immediately answer 202, which is different status code from 200. 200 means we did it, 202 means we've accepted it and we'll do it later. And which endpoints get this treatment is just config, so one extra flag per endpoint in the rule cell. Now, someone still has to actually do the park jobs, and that's the worker we have. It's about 10 lines, and all it does is pull a job off the list, do it, and repeat forever. We can notice how like the middleware and the worker will never talk to each other. One will drop the job into the list during the request, and the other will pull it out later. Okay, looks like we're done, but let me take a look at the finish diagram one more time. Okay, every single decision in the system flows through Redis, and that makes it a single point of failure. We need to consider what happens if it dies. Now, with the naive version, it'll throw an error, and that request will die with it. Then every request after will die the exact same way. So while Redis is down, the whole API will be effectively down. And this is called failing close. When the dependency dies, we reject everything. For some systems, that's the right behavior, but it's not really suitable for a rate limiter because some extra traffic is better than being completely down. So we need to make sure the API stays up, unprotected but alive. Okay, and that's the entire system done. Let's do one quick dry run end to end. So a request will come in through the only door. Nginx will pass it to one of the identical servers. The middleware inside will check its cached copy of the rules for that endpoint. Then it'll ask Redis to run the bucket map as one atomic operation. And either the endpoint runs and the response goes back with its budget printed on it, or it's a 429 with retry time. And if it's fire and forget work, then it'll get parked on the list and the worker will do it later. Lastly, if Redis itself dies, the API will stay up, unprotected, but it'll be alive.